Johannes Kepler looked at the data from Tycho Brahe for the motion of the planets, and he deduced three laws, which are the subject of what we're going to talk about here. Newton came along in 1687. Applied his three laws and his universal law of gravitation to prove Kepler's laws. G.E. Smith said of that proof, by the end of a century after the publication, after Newton's Principia in 1687, no one could deny that a science had emerged that, at least in certain respects, so far exceeded anything that had ever gone before that it stood alone as the ultimate exemplar of science generally. Also, Alexis Clairaut said, the famous book of mathematical principles of natural philosophy, that's Newton's work in 1687, marked the epoch of a great revolution in physics. The method spread the light of mathematics on a science which up to then had remained in the darkness of conjectures and hypothesis. Alexis Clairaut in 1747. So what we're seeing here is a snapshot in history that was incredibly important in the development of science. Suddenly, in 1687, we knew that we could apply mathematics to the study of nature, and we could get excellent results. So my objective here is to replicate what Newton did in proving these laws. The planets orbit the sun in ellipses with the sun at one focus. That's number one. We'll do it first. The radius vector from the sun to a planet sweeps out equal areas in equal times. We'll do that one second. And then finally, the period, the time for one revolution of the planet around the sun, squared, the square of the period, is proportional to the semimajor axis cubed. And semimajor axis is related to the radius. So without further ado, we are going to apply concepts 8.5 and 8.8 to do this. So first, planets orbiting the sun with in ellipses with the sun at one focus. Just a reminder of our polar coordinates. This is where we're going to be starting from. Distance from the sun to the planet, r. That's my radius vector that's discussed in the second law. Phi, the angle, measured from the x-axis. X is our cosine phi in polar coordinates, and y is our sine phi. And we're going to start from, let me number these equations. So I'll be referring to each of them in turn. So let me start from equation 2. And let me multiply equation 2 by 1 plus epsilon cosine phi. And that's supposed to equal c. All right? We write that a different way. R plus epsilon r cosine phi equals c. R cosine phi, that's just x. And r, we can get, big R, from the Pythagorean theorem. R squared equals x squared plus y squared. And so the r itself is the square root of x squared plus y squared plus epsilon times x equals c. I'm going to subtract epsilon x from both sides and then square both sides. So on the right side I get c minus epsilon x, on the left side I get the square root of x squared plus y squared, then square both sides, and I get x squared plus y squared equals c minus epsilon x squared. And then I'm trying to get this to look like the equation for an ellipse in Cartesian coordinates. Then I'm going to FOIL this out, distribute this. This will give me c squared minus 2 epsilon c x plus epsilon squared x squared. Then I'm going to subtract. I'm going to take this term and this term over to the left side of the equation. And when we bring this one over, it'll combine with this term to give me x squared times 1 minus epsilon squared. That takes care of that term and that term. And this term has a minus sign on the right-hand side of the equation. It'll be positive on the left. Then we end up with y squared okay. I want to complete the square. For reasons that'll become clear in just a minute. I'd like this to look like x squared over a squared plus y squared over b squared equals 1. That's the equation of an ellipse in Cartesian coordinates. And I've got an x squared here and a y squared here, but I've got this x term that's ugly. And the reason is that this equation is not centered on the center of the ellipse, but it's centered on one of the foci of the ellipse. So to complete the square, I'm going to divide through by 1 minus epsilon squared. That'll cancel this. And then I want to complete the square. And the way that I'll do that is to say x squared plus two epsilon c x over 1 minus epsilon squared. And then I want to know what term to add to this in order to complete the square. If I add the following term, yeah. So I'm going to add this term to both sides of the equation. Here I've added it to the left side of the equation. Then we have plus y squared equals c squared over 1 minus epsilon squared plus this term that I added to the left, I better add it to the right. All right, now this guy here is a perfect square. That's what I set out to do by completing the square. And it is x plus epsilon c over 1 minus epsilon squared, quantity squared. If you don't believe me, then FOIL it out. We get x squared, that's this term, plus 2 times x times epsilon c over 1 minus epsilon squared, that's this term, plus this term squared is epsilon squared c squared over 1 minus epsilon squared squared. So that's a happy day. And I forgot to, this y squared is over 1 minus epsilon squared. So let me correct that term. Okay. Plus now, the right-hand side is looking a little bit nice. We can factor out a c squared. And if we want to rationalize, want to get a common denominator, then I can multiply numerator and denominator of this first term by 1 minus epsilon squared. So what does that leave me? This first term, I'm going to factor out a 1 minus epsilon squared squared. I'll put it down here so I'll have room. Okay, so I want to factor out a c squared over 1 minus epsilon squared quantity squared. That's this guy here. In order for this term to look like that, I have to have a 1 minus epsilon squared. So then that one will cancel one of these and replicate this first term. And the second term is going to be, I've factored out the c squared over 1 minus epsilon squared squared, already factored out, and all we're left with is epsilon squared. So magically, I just get something really simple on the right-hand side. The epsilon squareds cancel, and I just get the c squared over 1 minus epsilon squared squared. So what I'm going to do now is define some constants. I'm going to define this constant here as d. I'm going to define, actually no, yes I am. And I'm going to I'm going to define this as a squared. And then we're going to define a b in just a second. So a is going to be defined as c over 1 minus epsilon squared. B I'm going to define as square root of c times a. So that, I'm just defining constants here. Square root of c times a, that will give me square root of c squared over 1 minus epsilon squared, and that's just c over the square root 1 minus epsilon squared. And then I'm going to define d let me move that down for fear of running out of space. We're going to define that to be epsilon c over 1 minus. All right, let's see what we have now. X plus d squared plus y squared over 1 minus epsilon squared equals a squared. We're almost there. It's a lot of work. But one reason I'm going through this exercise is that you'll have an exercise that you need to go through for hyperbolic orbits that's almost identical to this, where you need to complete the square, etc. All right, this is starting to look like, we're looking very close to the equation for an ellipse in Cartesian coordinates. But normally, the equation for an ellipse will have an x squared over a squared plus y squared over b squared equals 1. And we don't have a 1 on the right-hand side. So let me divide both sides by a squared. Then what does it look like? X plus d squared over a squared plus y squared over a squared times 1 minus epsilon squared. And that's supposed to equal 1. But this is just going to be b squared. And how do I know that? It's the easiest way to see it. A squared is going to be c over 1 minus epsilon squared. So if you substitute that in here, you'll have c squared over a squared is c squared over 1 minus epsilon squared. And that's b squared, right there. So sorry, I had a little brain cramp there to see where it came from. But if we have, we put this a in here, we'll have a c squared over 1 minus epsilon squared. So we'll end up with c squared over 1 minus epsilon squared, and the square root of that is just b. If you don't believe me, do the algebra. This is an ellipse with the origin at one focus. And if you want to, so in other words, let's see. X, Y, A, B, D. So this is the center of the ellipse. This is one of the foci. And there's another focus here. So the note here also that D is epsilon times A. Here A is c over 1 minus epsilon squared. And that's one of the characteristics, that's in fact how you define the eccentricity, is this distance between the center of an ellipse and one of the foci is the eccentricity times the semimajor axis. So A here is called the semimajor axis. B is called the semi-minor axis. If you don't believe that that's really an ellipse, then just say, let me define x prime as x plus d. And y prime as y. And then substitute both of those into here. Well, what do you get? X prime is x plus d, that'll be x prime squared over a squared plus y prime squared over b squared equals 1. And that describes an ellipse that is centered. So this is an ellipse centered at the origin. So in this case, if you look at it in this way, this is more familiar. You might have seen this in high school geometry. Then the center is right here of the ellipse that coincides with the original coordinates, and then the two foci the plural of focus is foci. Those are a distance d away from the center. A again is a semi-major axis. Y or B is a semi-minor axis. The semi-major axis is the distance from the center of the ellipse to the along the widest portion of the ellipse. It's half the diameter. That's why they call it a semi-major axis. You call the major axis would be just this distance 2a, and the minor axis would be that distance 2b, and semi means half of that axis. So that is the proof that planets orbit the sun in ellipses with the sun at one focus. And given the fact that we've used up the board here, I'm going to erase the board and then continue the video for numbers 2 and 3. Okay, here's what we have so far. We have an ellipse with a semi-major axis A. Here's the center of the ellipse, this dot in the middle of the 3 dots. And semi-minor axis B, and then a distance from the center of the ellipse to one of the foci being D, and those are given by these equations, where C is this constant here, which involves the angular momentum, and epsilon is the eccentricity. So you'll see that if epsilon equals 0, we talked about in a previous concept, if epsilon equals 0, there's no eccentricity. Eccentricity is equal to 0. D is equal to 0. The two foci actually coincide with the center of the circle, and it's a circle instead of an ellipse. So that's how that one comes out. We're now going to consider the second law, the radius vector from the sun to a planet sweeps at equal areas and equal times. So we'll need a diagram for this one. So here's the origin coordinates at one of the foci. Remember the origin, this coordinate system is centered on the focus to the right. So here's the center of the ellipse and here's the other focus. This coordinate system is centered on the focus on the right side of the center. So this distance here is the minimum radius, and this distance here is the maximum radius. So this radius vector is sweeping out The claim is that it sweeps out equal areas in equal times. So let me consider that area. Let me consider this to be the position of the planet at time t. And then as it's going around, this would be the position of the planet at time t plus delta t, or t plus. So it's gone that distance in a time delta t. What's the area swept out? Well, this distance from the origin to that location is called r, and the area swept out is going to be the area of this triangle. Well, it's effectively a triangle between the origin, this point, and that point. And as delta t gets shrunk to 0, then the curvature of this line won't matter, and the area should be given by that area of the triangle. Well, the area of a triangle is 1/2 the base of the triangle times the height of the triangle. And if we take the base of the triangle to be this r right here, then the height of the triangle should be this distance right here, h. But that distance is given by r times the angle through which it has swept. So this is the angle delta phi that is swept out in that time. That's the angle that we're talking about here. It's sweeping out an equal area in an equal time. Well, now amazingly, we can divide through and take the limit as delta, as this time interval goes to, well, let me go ahead and put it in. Delta A divided by delta t. So I'm dividing both sides by delta t equals 1/2 r squared delta phi divided by delta t. So I've just divided by the change in time. In the limit that delta t goes to 0, this finite difference can be we can replace it with a derivative and d phi by dt is just phi dot. And amazingly, we know what phi dot is from equation 1. Phi dot is L over mr squared. So lo and behold, amazingly, the r squareds cancel. This r squared kills this one, and we get L over 2m. What does that say? It says that the area swept out divided by the time is a constant. It doesn't depend on where you are in the orbit. So you've got to be able to sweep out an equal amount of area when you're close as when you're far. Here you're far away, and that area had better be the same as the area that you sweep out when you're close, assuming that the delta t is the same in both cases. What does that say about the speed of the planet as it orbits the sun? It says that in order for you to get the same amount of area here as here, well, let me just use the same notation, delta A and delta A. As long as those, in order to make those areas to be the same, you have to be moving faster here. You have to be going through a greater angle because the distance is shorter and that area has to be the same. It's amazing that Kepler figured that out. I don't know. Looking at sometimes flawed data of Tycho Brahe, and yet Kepler figured out that second law. So this says that the radius vector from the sun to a planet sweeps out equal areas in equal times, and that area swept out as a function of time is L over 2m. So that proves the second law, and let's see if we can do the third law. And it's not hard. The third law is the period, the time for one revolution. And we can use the second law to prove the third law by saying that by integrating over one full period. So what we're going to do is to rewrite this as dA is L over 2m times dt. And then integrate over one period. Well, if you integrate over one period, so you're going to start with phi equals 0 and go all the way around to your back at phi equals 0 again. So that'll just give the total area of the ellipse is L over 2m times the total time that it requires to go around. Well, that's what we call the period, tau. That's the time for one complete revolution. But we also happen to know the area of an ellipse. And you could look it up. I had to look it up, and in fact you can prove it. You can do the integral yourself if you haven't done it in a while. But the area of an ellipse is pi. It looks like the area of a circle. The area of a circle is pi r squared. But the area of ellipse is pi times A, the semimajor axis, times B, the semi-minor axis. So if we now solve this for the period, we're going to multiply both sides of this equation by 2m over L. And then multiplied by A, the area of the ellipse. And then we're going to substitute we're going to use this equation. Let me call this equation 4. And plug that in for B, square root of C times A. I'd like all these expressed in terms of A. And then I'm also going to use equation 3. But let me substitute equation 4 in first. So we put equation 4 in. We got 2m over L pi times A times B, which is the square root of C times A. And then for anticipating that it's going to be the square of the period that's related to the cube of the semi-major axis, I think you can start to see it right now. Let me square both sides of this equation. Times pi squared times A squared times the square root of CA squared, just CA. And then I'm going to invoke equation 3 to get rid of the C. For pi squared m squared over L squared times C, and C is L squared, over GMM squared times A cubed. We've got an A cubed here because we've got A squared there times A makes A cubed. Now notice what happens here. This is amazing. I got an L squared numerator and denominator. They cancel. I got an M squared numerator and denominator. They cancel. And we're left with and that, my friends, is Kepler's third law. The period squared is proportional to the semimajor axis cubed for all the planets. This constant of proportionality this constant is the same for all the planets. Well, how do I know that? Well, it depends only on the Newton's universal law of Newton's universal gravitational constant, G, and M, and that's the mass of the sun. So all these planets are going to have that same, and be subject to the mass of the same sun, and they should all obey this relationship. So shown, and remarkably, the little m canceled out. So what does that say in terms of orbiting around the sun? That means that you could replace the Earth in its orbit with a baseball with the same speed. If it's in the same position and going at the same speed, that baseball would still take 1 year to go around the sun. You say, how so? Because it weighs a lot less, the mass is a lot less. And I say, yeah, those effects cancel out. It still has, the gravity is less, but it has less momentum or less inertia, and you end up, so any object at the location of the Earth and orbiting at the same speed will still orbit the sun in the same amount of time, period. So shown here is a plot of the period squared as a function of the semimajor axis cubed for all 9 planets, including Pluto. Well, let's say it's all planets, plus some minor planets, Pluto and some asteroids, Ceres, etc., where I actually looked up the data for the periods for all of these and the semimajor axis of their elliptical orbits and crunched the numbers and made this plot. And the remarkable thing is how very amazingly close they come to a straight line, meaning that that constant of proportionality, 4 pi squared over gm, is going to be the same for all of them. They all lie on the same line. So as we mentioned before at the beginning of this concept, this is one of the greatest triumphs of physics, to show that these planetary orbits obey laws, mathematical laws, that can also relate to other things. Newton's 3 laws don't only apply to the motion of the planets, they apply to pretty much everything. And the fact that you can apply logic and mathematics to understand our world is an amazing thing.